In this video, I'm going to go over our topic for Unit 3, Section 3, Part 1, and that is VSEPR or VSEPR Shapes. First, we're going to go over a review of Lewis dot structures. So how do Lewis dot structures help us, and what are the limitations of Lewis dot structures? Next, we'll go into this VSEPR theory, or VSPER, talk about what molecules look like in 3 dimensions. We're going to talk about the shapes that we use for VSEPR theory and the different rules we use to create those shapes. And finally, we'll talk about complex structures or what large molecules look like. So that being said, let's do a quick Lewis dot structure review. Remember that Lewis dot structures are just two-dimensional representations of how atoms are connected. So if I look at this molecule on the right of H2O, it gives that water molecule, or H2O, on a flat plane. These are simplified Bohr model configurations, so we're only talking about the valence electrons. And remember that atoms only bond at the lone electrons. So we can still have these pairs of electrons, they just kind of hang out on the atoms. And our configurations are complete, our Lewis dot structures, when all the atoms in the molecule are connected and every atom has an octet, meaning that most atoms have 8 electrons in their immediate area, except for things like hydrogen, which are content with just 2, remembering that 2 electrons are in each covalent bond. So that being said, what are the limitations of Lewis dot structures? Remember that Lewis dot structures, they're only going to show us the connections between atoms, but they don't show us the shape. On the left, we have our Lewis dot structure for CH4, or carbon tetrahydride. On the right, we can see this three-dimensional representation, and that's where we need to head next. What do our molecules look like in 3 dimensions? And that's where VSEPR theory comes in. So what VSEPR theory is it stands for valence shell electron pair repulsion. But basically what's going to happen is the valence electrons on all of these atoms are going to repel each other, except for the ones involved in bonding. So remember that atoms are all surrounded by a sea of valence electrons, and what this boils down to is that every group attached to a center, in this case all of the hydrogens, are going to want to be as far apart from the center as possible, or as far apart from each other as possible. These hydrogens in 3-dimensional space are going to move away from each other to just occupy the most space possible and just kind of get away from one another. Really, what it allows us to do, as I mentioned before, is take this 2-dimensional structure, this CH4 that's flat on the page, and view it as this 3-dimensional molecule. Let's talk about how we do that. Remember, though, that atoms connected to the center atom always have to be as far apart as possible, and know that these lone electron pairs, such as on this NH3 on the bottom right, they also repel other groups. They kind of act like a fourth atom, even though they're not really massive. They don't act like an atom in that they don't interact with other atoms really, but they do kind of take up this area. So they don't take up space in terms of a physical sense, but they do push the other atoms away. So if I really quick step back, notice that these Lewis structures, each of these molecules has 4 total groups attached. This carbon has 4 hydrogens, and this nitrogen has 3 hydrogens and 1 lone electron pair. So they both sort of have the same 3-dimensional shape. We can see the CH4 shape on the right and the left. And the NH3 has the same shape, except this top group is no longer a hydrogen. It's now just taken up by the space of the lone electron pair. So imagine this lone electron pair hanging out on top of this molecule. It would end up being a similar shape to CH4, just the lone electron pair we don't represent in the drawing. Really quickly, one other note. Double and triple bonds in VSEPR theory are going to act the same way as single bonds because we only care about the attached groups. So this BeH2, the single bonds in this are going to give us the same structure as CS2 because we still have 2 things attached. Also notice that these S's have these lone pairs, but that does not influence the geometry around this carbon because the lone pairs are not attached to the carbon. The geometry is only concerned with what's attached to this center atom. All right, let's go through a quick review of the shapes and the rules. The most simple shape is this linear shape, and that's when we have two things attached to a center. We actually looked at this on the previous slide. We have carbon in the center, and we have two atoms attached to it. So this gives us two atoms in a line. Those sulfurs are as far apart from the carbon as possible. We actually have a format, we call it AXE formula, for saying what kind of shape this is. The A in this case represents the center atom carbon, and these two X's represent the two atoms attached to carbon. And we call this linear because these molecules are in a line. Next, if we add one more group, we call this shape, one carbon with three attached groups, trigonal planar. And we call it that because we have three attached groups, that's the trigonal, and we call it planar because this is indeed a flat molecule. The farthest these groups can get apart from one another is to lie flat in a plane. Looking at our AXE notation, just like before, our A is our center atom, and our three attached atoms are our X3. So AX3 represents this VSEPR shape. Now is when things get interesting. When we have four groups, we call it a tetrahedral arrangement. Notice these four hydrogens are attached to the center carbon. And when we say tetrahedral, tetra does stand for four, but hedral actually refers to the three-dimensional shape created if we attached all of these hydrogens together. And I'll show that on the next slide. Before I show that though, notice that our AXE formula follows the same pattern. A for the carbon and X4 for the four hydrogens. And let's look at this tetrahedral molecule in three-dimensional space. Notice here that if I connect all the hydrogens with a three-dimensional shape, it forms this four-sided pyramid. Three faces up here on the top, and then this one base on the bottom. And this is our tetrahedral arrangement. Now notice, if we do what we said in a previous slide, and we replace one of those groups with an electron pair, we get a different kind of shape. Our formula changes. Instead of having AX4, we now have AX3, the nitrogen with three hydrogens, and we have to add this E right here, representing the electron pair. This does change our shape. We are no longer tetrahedral. We still have this little kind of pyramid shape, but there's no group coming out of the top. And this is going to form something called trigonal pyramidal. It forms a different pyramid than what is in trigonal planar, tetrahedral. If I look at the next shape, we can see the tetrahedron would be if we use the lone pair, but we don't, so we get this squat sort of pyramid, and that is our trigonal pyramidal shape. We can do the same thing, but replacing two of the hydrogens with lone pairs. Now we get AX2E2, sulfur with two hydrogens and two electron pairs. And this forms a flat molecule, but it's actually bent at an angle, and we call this the bent structure. So just like before, the tetrahedral arrangement is there if we counted the electron pairs, but when we don't and we just look at the molecule itself, it just forms this bent shape. And there are two more exotic examples I'm going to point out now. We went over these very briefly in our last section. If we look at five attached groups, this happens very rarely, but if we have one center atom and five attached groups, we have a trigonal bipyramidal shape. We have these two pyramids kind of attached at the base. So they're like our trigonal pyramidal shapes, but there's two of them, therefore trigonal bipyramidal. And we can also have six groups. And you might think, oh, again, this is two pyramids on top of one another. But whenever we have one atom in the center and six attached groups, we actually call this octahedral because we get this shape at the bottom left where it is one shape with 8 equal faces, all triangles. And so we call this octahedral. Very quickly, let's talk about complex structures. In chemistry, many large molecules can have a ton of central atoms. And so we get these huge structures that look very difficult at a glance. However, if we focus at any central atom, we can look at it through VSEPR theory and say what kind of shape it has. For example, if I look at this relatively simple molecule, C with 3 H's attached and an N attached, and N with 2 H's, 1 C, and a lone electron pair, I can look at each of these central atoms and say what the shape around that atom is. Looking at the carbon, it looks like it has 4 atoms attached. Therefore, its formula would be AX4, and it is tetrahedral. And if we just focus on the carbon in the bottom left, we can see that the shape around carbon is indeed tetrahedral. If we look at the N, it seems like it has 3 atoms attached and 1 electron pair. And that gives us AX3E, which is our trigonal pyramidal shape. And again, if we just focus in on the blue nitrogen on the bottom left, we can see that it forms that trigonal pyramidal shape, that squat pyramid with the carbon and 2 hydrogens as its kind of like base legs. And that is it for Lewis dot structures. I hope this presentation helped you understand VSEPR theory and how it relates to Lewis dot structures a little bit better.